In the previous lecture, we have been talking about the fundamental basics of array data structures. In this lecture, we are going to talk about the concrete operations. So for example, the first case we are going to consider is when we want to insert a new item at the end of the data structure until the data structure is not full. And it is a fast operation. It has order 1 constant running time complexity. So what do we have to do? Basically, we just have to insert the items at the end of the array data structure. You may pose the question that what's going to happen if the data structure becomes full? First of all, we have to allocate a larger chunk of memory in the RAM, usually twice the size of the actual array, and we have to copy all the existing items one by one to the new array. And because of these operations, the resize takes order n linear running time complexities. So this is the bottleneck operation as far as arrays are concerned. So there is a huge trade-off between the amount of memory we use and the running time of the given data structure, because if we start with a small array, then we do not waste memory, but we have to resize the array often with order n linear running time complexity. On the other hand, if we allocate a huge array at the beginning, then we do waste memory because of the large size, but at least we don't have to bother with the resize operation. This is a typical trade-off in computer science as for memory and running times are concerned. If we want to make an algorithm fast, then we have to make sure that the algorithm uses more memory. If we want to minimize the amount of memory the given application uses, then the running time complexity is not going to be the best one possible, which means that the algorithm is going to be slower. So we can boost up the running time of an algorithm with the help of extra memory. So we can come to the conclusion that we can make a given application faster with additional memory. Okay, what if we would like to insert a new item to an arbitrary position? So we want to insert an item associated with a given index. For example, we would like to insert a new value with index 1. Of course, there's already an item, so what do we have to do? First of all, we have to shift every single item that has higher index values than the actual one. So what does it mean? The 25 will be shifted, -7 will be shifted, 5 will be shifted, and then we are able to insert the new value. This operation has order n linear running time because the items must be shifted, and in worst case scenario, if we want to insert a new item with index 0, then we have to shift all the items. So this is why inserting an item with a given index has order n linear running time complexity, which is not that favorable. What if we would like to remove the last item from an array data structure? Again, it is quite fast. We can do it in order 1 constant running time complexity. So for example, we have these values and we would like to remove the last item, we just have to remove it. Again, we would like to remove the last item, we just have to remove -7, and so on. So removing the last item again is quite fast. Then what about the last case? We would like to remove an item from an arbitrary position. Usually, we do not know the index of the item we would like to remove. And the second problem is that after removing the item, we have to deal with the so-called holes in the data structure. Okay, so for example, we would like to remove the number 5. First of all, we have to search for that given item. It is going to be an order n linear running time operation. Then after removing the item, it is the so-called hole in the data structure. So as you can see, it is not favorable. So what do we have to do? We have to make sure that the items are going to be shifted one step upwards. So first we have to find the item with order n running time, and then we have to remove that given item, which is quite fast, but then we have to shift the items again in order n linear running time complexity. So this is why the overall running time complexity, as far as removing an arbitrary item from an arbitrary position, is going to have linear running time complexity. So we can come to the conclusion that if we want to manipulate the last item of an array data structure, whether we insert a new item or we remove a given item, then it is going to be fine. This is why we like arrays. But if we want to manipulate arbitrary items, whether we are inserting new items at arbitrary positions or remove a given item from an arbitrary position, these operations will have ordo and running time complexity. So we can come to the conclusion that if these kinds of operations will dominate in our application, then array data structure may not be the best option possible because of this linear running time complexity. We can do better than linear running time. So let's summarize the advantages of arrays. The best features of arrays is the so-called random access, that we can access arbitrary items extremely fast if we know the index. It is quite an easy data structure, easy to understand and easy to implement from scratch. Arrays are considered to be fast data structures, and we have come to the conclusion that array data structure is working extremely fast if we manipulate the last items of the data structure, or when we want to access items with known indices. What about the disadvantages? We have to know the number of items we want to store at compile time, so basically arrays are not dynamic data structures. Since they are not dynamic, whenever this data structure is full, we have to resize it. That has ordo and linear running time, which is not that favorable. At last, the problem with arrays is that they cannot store items with different types. This is the case when we are dealing with C, C++ or Java, but as far as Python is concerned, we can store items with different types. This is why Python is so convenient. So Python is quite powerful because we can store items with different types, but it is not that usual for arrays. In the next lectures, we are going to talk about concrete examples as far as lists and arrays are concerned. Thanks for watching.